code statement specifying an additional load of 150 volt amps for every 2 feet of track means that you must add this value to the total connected load of the track heads themselves. This additional load accounts for the inherent electrical demand the track lighting system presents beyond the individual amps. This requirement applies irrespective of whether you are utilizing Table 220.3 for overall service size calculations or not. To determine the lighting load on a panel that incorporates track lighting, follow these steps. Firstly, sum the connected load of all track heads attached to the track lighting system. For example, if you have 20 track heads, each drawing 75 volt amps, the initial load is 20 multiplied by 75, which equals 1500 volt amps. Secondly, ascertain the total length of the track lighting in feet and divide by 2. Then, multiply the result by 150 volt amps. This calculation yields the additional load imposed by the track. For example, if you have 30 feet of track, divide 30 by 2, which equals 15. Multiply 15 by 150 volt amps, resulting in 2250 volt amps. Thirdly, add the track head load to the additional track load. In the prior examples, add 1500 volt amps, which was the load of the track heads, to 2250 volt amps, which was the calculated track load. The result equals 3750 volt amps. Finally, include this total to the load of any other lighting fixtures connected to the same panel. Assume there are additional recessed lights drawing 600 volt amps. Add this 600 volt amps to the 3750 volt amps of the track lighting, which equals 4350 volt amps. Consider another detailed example. Imagine a panel feeding track lighting with 15 track heads, each rated at 60 volt amps, and a track length of 24 feet. To calculate the lighting load, follow these steps. Calculate the track head load, which is 15 multiplied by 60 volt amps, totaling 900 volt amps. Calculate the track load by dividing the total track length by 2, thus 24 feet divided by 2, which equals 12. Then multiply this value by the code mandated 150 volt amps per 2 feet. 12 multiplied by 150 volt amps equals 1800 volt amps. Combine the track head load and the track load by adding 900 volt amps to 1800 volt amps, resulting in a total of 2700 volt amps. Incorporate this total load with any other lighting connected to the same panel. If additional lighting totaling 1000 volt amps is present, add this to the 2700 volt amps, resulting in a total lighting load of 3700 volt amps for the panel. To further illustrate, let's consider a scenario where you have 8 track heads, each with a consumption of 75 volt amps, connected to 16 feet of track. Firstly, calculate the total load of the track heads. This is achieved by multiplying the number of heads by their individual volt ampere rating. So, 8 multiplied by 75 volt amps equals 600 volt amps. Secondly, determine the additional load imposed by the track length. Divide the total track length by 2, and then multiply by 150 volt amps. In this case, 16 feet divided by 2 is 8, and 8 multiplied by 150 volt amps equals 1200 volt amps. Thirdly, sum these two values. The total track lighting load is the sum of the track head's load, 600 volt amps, and the track load, 1200 volt amps, which equals 1800 volt amps. If, for instance, this track lighting circuit is connected to a panel that also feeds a set of decorative sconces with a combined load of 400 volt amps, then the total lighting load on the panel would be the sum of the track lighting load, 1800 volt amps, and the sconce load, 400 volt amps, totaling 2200 volt amps. Let's take a closer look at how these calculations translate into practical electrical design. In electrical design, accuracy is vital to ensure safety and code compliance. Let's consider another comprehensive example. Suppose you are designing a lighting system for a retail space. The design includes 25 track heads, each rated at 50 volt amps, and a total track length of 40 feet. The panel also supplies power to 6 recessed can lights, each consuming 75 volt amps. Firstly, calculate the total volt ampere load of the track heads. This is the number of track heads multiplied by the volt-ampere ratio of each head. Thus, 25 multiplied by 50 volt-amps equals 1250 volt-amps. Secondly, determine the additional volt-ampere load imposed by the track lighting. According to code, you must account for 150 volt-amps for every 2 feet of track. Divide the total track length 40 feet by 2 to get 20. Then multiply 20 by 150 volt-amps, resulting in 3000 volt-amps. Thirdly, sum the volt-ampere load of the track heads and the track lighting. This gives you the total volt-ampere load for the track lighting system. Therefore, 1250 volt-amps plus 3000 volt-amps equals 4250 volt-amps. Finally, add the volt-ampere load of the recessed lights to the total track lighting load. The recessed lights consume 6 multiplied by 75 volt-amps, which is 450 volt-amps. Adding this to the track lighting load, 4250 volt-amps, gives you a total lighting load on the panel of 4700 volt-amps. To ensure the circuit is not overloaded, you need to consider the continuous load. According to the National Electrical Code, branch circuits shall be calculated at not less than 125% of the continuous loads plus 100% of the non-continuous loads. If this lighting load is considered a continuous load, meaning it operates for 3 hours or more, you will need to increase the calculated load by 25%. For example, if the total lighting load is 4700 volt-amps, you would multiply this by 1.25, resulting in a design load of 5875 volt-amps. This adjusted value is critical for proper circuit breaker sizing and wire gauge selection. Choosing the appropriate wire gauge is essential for safely carrying the electrical current. The American wire gauge (AUG) system is a standard for wire sizes, and each gauge has an ampacity rating indicating how much current the wire can safely handle. Table 310.15b16 of the NEC provides ampacity ratings for various wire sizes based on insulation type and installation conditions. For example, if a circuit requires a 20 amp overcurrent protection device, you would typically use 12 AWG copper wire with THHN insulation, which has an ampacity of 20 amps under certain conditions. However, if the wires are bundled or run through insulated walls, their ampacity might need to be derated according to NEC guidelines. Overcurrent protection devices, such as circuit breakers or fuses, are designed to protect electrical circuits from overloads and short circuits. They interrupt the flow of current when it exceeds a safe level, preventing damage to equipment and reducing the risk of electrical fires. The selection of the correct size of overcurrent protection device is based on the ampacity of the conductors and the load they serve. The NEC provides rules for selecting the appropriate overcurrent protection for different types of circuits and equipment. For example, a 20 amp circuit breaker is typically used for general lighting and receptacle circuits in residential and commercial buildings, while larger breakers are used for higher demand appliances and equipment. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause lights to dim, motors to overheat, and equipment to malfunction. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, you can use larger conductors or shorten the length of the circuit. Calculating voltage drop involves considering the conductor's resistance, the current flowing through it, and the length of the circuit. Online voltage drop calculators and NEC tables can assist in these calculations. Proper grounding and bonding are crucial for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and to energize the circuit. Bonding connects non-current carrying metal parts of electrical equipment together to create a lower impedance path for fault current. The NEC specifies requirements for grounding and bonding, including the size and type of grounding and bonding conductors, and the methods for connecting them. Properly grounded and bonded electrical systems help to prevent electric shock and reduce the risk of electrical fires. The NEC is updated every 3 years to reflect changes in technology, safety standards, and industry best practices. Staying current with the latest edition of the NEC is essential for electrical professionals to ensure compliance and maintain safety. Many jurisdictions adopt the NEC as their electrical code, while others may modify it to suit local conditions. It is important to be familiar with the specific electrical codes and regulations in your area. Continuing education and training are crucial for electrical professionals to stay up to date with the latest codes, standards, and technologies. Many organizations offer courses, seminars, and certifications to help electricians and electrical engineers maintain their skills and knowledge. Investing in continuing education can improve your career prospects and ensure that you are providing safe and compliant electrical installations. Remember to always consult the latest edition of the NEC and local electrical codes for specific requirements and guidelines. Electrical work can be dangerous, and it is important to take precautions to protect yourself and others. Always de-energize circuits before working on them, use appropriate personal protective equipment, and follow safe work practices. If you are not qualified to perform electrical work, hire a licensed electrician to do the job. Electrical safety is everyone's responsibility. If you see something that looks unsafe, report it to the appropriate authorities. By following safe electrical practices, we can prevent accidents and save lives. Let's reinforce these concepts with an additional example. Consider a commercial office space that utilizes track lighting. There are 30 track heads, each consuming 65 volt amps, and the total track length measures 50 feet. The panel also powers fluorescent lighting with a load of 1800 volt amps. Firstly, determine the total load of the track heads. Multiply the number of heads, 30, by the volt amps per head, 65 volt amps, resulting in 1950 volt amps. Secondly, calculate the additional load for the track. Divide the total track length, 50 feet, by 2, yielding 25. Multiply this by the standard 150 volt amps per 2 feet of track. 25 multiplied by 150 volt amps equals 3,750 volt amps. Thirdly, combine the track head load and the track load. Adding 1950 volt amps to 3,750 volt amps gives you 5,700 volt amps. Finally, add the fluorescent lighting load to the track lighting load. Add 1800 volt amps to 5,700 volt amps, totaling 7,500 volt amps. If the lighting is considered a continuous load, apply the 125% factor. 7,500 volt amps multiplied by 1.25 results in 9,375 volt amps. This value is used for selecting the appropriate wire size, conduit fill, and overcurrent protection for the lighting circuit. Furthermore, consider the impact of ambient temperature on conductor ampacity. If the ambient temperature exceeds 30 degrees Celsius, 86 degrees Fahrenheit, the ampacity of the conductors must be derated according to NEC Table 310.15b2. For example, if the conductors are rated for 90 degrees Celsius and the ambient temperature is 40 degrees Celsius, the ampacity derating factor would be 0.91. This means that the conductor's ampacity is reduced to 91% of its listed value. Derating factors are also applied when multiple current-carrying conductors are bundled together in a raceway or cable. When more than 3 current-carrying conductors are installed in a raceway or cable, the ampacity of each conductor must be reduced according to NEC Table 310.13b3. The derating factor depends on the number of conductors and the type of insulation. For example, if there are 7 to 9 current-carrying conductors in a raceway, the ampacity derating factor is 0.70. This means that the ampacity of each conductor is reduced to 70% of its listed value. Understanding and applying these derating factors is essential for ensuring that conductors are not overloaded and that electrical systems operate safely and reliably. Always consult the NEC for the latest requirements and guidelines on conductor ampacity and derating factors. In summary, calculating track lighting loads involves several steps. Firstly, determine the total load of the track heads. Secondly, calculate the additional load imposed by the track length, using the 150 volt amps per 2 feet rule. Thirdly, sum these two values to obtain the total track lighting load. Finally, add this load to any other lighting or electrical loads on the same panel to determine the total panel load. Always remember to consider continuous loads and apply the 125% factor if necessary. By following these steps and consulting the NEC, you can ensure accurate and safe electrical installations.